All right, let's dive in. Today, we're going to pull back the curtain on one of the coolest, most intelligent systems keeping modern video games from, well, completely falling apart. We're talking about a huge shift in how game engines handle graphics, a move away from code that's basically one typo away from disaster, to systems that are almost impossible to break.
But that makes you wonder, right? Why were things so fragile in the first place? I mean, when you see this absolutely stunning, complex world rendered on your screen, you're probably not thinking about the million different ways it could have all gone wrong. But for developers, oh yeah, that risk is very, very real.
You know, for a long time, building a rendering pipeline, it was like trying to walk through a minefield. Seriously. One wrong step, one single command out of order, and the whole thing could just blow up right in your face. And this wasn't because of bad programmers. It was because the entire philosophy behind it was kind of flawed from the start.
So the main culprit here was a technique called deferred rendering. Now, don't get me wrong, it was a massive leap forward. It gave us all this incredible dynamic lighting we love, but it came at a huge cost. It basically splits the rendering into all these different stages, and the developer, well, they had to manually keep track of absolutely everything. When was this texture written to? When is it being read from? And you better pray the GPU doesn't try to do both at the exact same time.
This whole situation created the single most common, most frustrating, hair-pulling bug in the entire system, the missed barrier. A barrier is really just a simple command that tells the GPU, hey, hold up, finish what you're doing right here before you even think about starting the next thing. It's a synchronization point, and if you forget just one,
you get total chaos. We're talking flickering shadows that just pop in and out of existence, ghost pixels from old frames hanging around, or even worse, a complete GPU hang that just crashes the entire game. And tracking these bugs down, it's a nightmare because they can be totally random and almost impossible to reproduce. Developers were spending a huge chunk of their time just trying to prevent these kinds of errors.
But what if you could just get rid of that entire category of bugs? Just poof, gone. Well, that's where the hero of our story comes in, the frame graph. This is a completely new way of thinking. It's a declarative solution to what was an old, messy, imperative problem.
The whole idea, which Yuri O'Donnell put so brilliantly at GDC, was to stop telling the GPU how to do its job, step by painstaking step. Instead, you just describe the final result you want, and you let a much smarter system figure out the most efficient and, crucially, the correct way to get there. It's basically like a compiler, but for your rendering.
And the backbone of this whole system is something called a directed acyclic graph, or a DAG. Now, don't worry about the fancy name, the concept is actually pretty simple. Think of each step in the rendering process, like drawing shadows or calculating lighting, as a little node, a bubble. The lines connecting them are the resources they share, like textures. This graph structure makes it mathematically impossible for a step to depend on itself, and it guarantees that everything happens in a perfectly logical order. So, let's do it. Let's put the old way and the new way head-to-head. How does this automated, graph-based approach really stack up against that manual minefield of deferred rendering? This slide just lays it all out, doesn't it? It perfectly shows the old pain points versus the new solutions. So where developers used to have to manually stick in every single one of those barriers by hand, the frame graph just infers them automatically. It looks at all the dependencies and just knows exactly where to put them. Which means all those nasty race conditions and synchronization bugs, they're just gone. It's a system that's correct by its very design. And the real-world impact of this is just huge. An entire class of bugs just completely wiped off the map. This doesn't just make the final game more stable, it gives a massive amount of time back to the programmers. They can spend their energy making the game awesome, not hunting for a single misplaced command.
Now, the frame graph doesn't just solve synchronization, it also tackles another huge headache, managing all that memory on the GPU. The system just keeps getting smarter, going from solving timing bugs to solving resource management.
Think about it. Manually allocating and freeing every single texture and buffer on the GPU is just as error-prone as manual synchronization. So, by plugging an intelligent system like the Vulkan memory allocator, or VMA, right into the graph, just how much better did things get?
A 98% reduction. No, that is not a typo. Instead of making thousands of tiny, slow memory requests to the graphics driver, the system now makes just a few big ones and manages all the little pieces itself. This means you're not hitting hard driver limits, and the whole thing is just way more efficient. And on top of that, it's way smarter about how it uses that memory.
In this test case, having the VMA work with the frame graph's knowledge of when resources are born and when they die led to a 24% drop in total VRAM usage. It reclaims memory the instant it's no longer needed, which is something that's incredibly difficult to do perfectly by hand.
So, what this all really comes down to is a massive philosophical shift in engine design. It's all about focusing on your intent, not the individual commands.
The old imperative way was all about telling the system exactly how to do everything, step by step. The new declarative way is about telling the system what you want to achieve. You describe your goal, you list its dependencies, and you trust the system to figure out the best way to get there. It's really the difference between giving someone turn-by-turn directions versus just plugging a destination into your GPS and letting it do the work.
And in practice, this makes the developer's job incredibly clean. You just define your rendering passes, you declare what resources they need to read from and write to, and then you just tell the graph to compile and run. All those messy, painful details of barriers, memory layout transitions, and allocations are completely handled for you.
Look, this isn't just some neat programming trick. This is the future of high-performance engine design. So let's just quickly recap the key takeaways from this whole transformation. At the end of the day, this declarative approach is a total force multiplier. It radically improves developer productivity by simplifying the code they have to write, it dramatically increases memory efficiency, and maybe most importantly, it delivers automatic correctness, building this super strong foundation of reliability that every other system in the game can be built on top of.
And that leaves us with a really fascinating final thought. This whole shift, from telling the computer how to do its job to just telling it what we want, that's a really powerful pattern. Now that it has completely transformed rendering, you have to wonder, what other complex, error-prone parts of development are next in line for their own declarative revolution?